We're now going to see a little bit different mechanism in the ozonolysis and dihydroxylation of alkenes. So the first one that we're going to take a look at is ozonolysis. And ozonolysis, as the name implies, is a reaction of an alkene with ozone. Ozone, if you recall, O3, is what we call a 1,3 dipolar reagent. Now, how do we get that term? Looking at the Lewis structure of ozone, we see, and you should be able to draw the Lewis structure of ozone, right? I remember doing this in general chemistry. So one of the oxygens has a negative charge, and the oxygen in one of the oxygens on the side has a negative charge, and the oxygen in the middle has a positive charge to it, right? So overall, it's a neutral compound. And obviously, this has a resonance structure where we can put the negative charge onto the oxygen on the right-hand side. We typically see these two resonance structures in ozone and how we represent ozone. However, there is a third possible resonance structure that usually isn't talked about, and that is if I simply donate a pair of pi electrons onto the central oxygen. Now that oxygen is electron deficient, so if you think about if I donate electrons onto that central oxygen, the result looks like this, where I now have two pair of electrons on the central oxygen. It becomes neutral. The oxygen on my right is still negative. The oxygen on my left now doesn't have an octet of electrons, but it takes on the positive charge. This is where we get the term 1,3 dipolar reagent. So that oxygen has a partial positive charge, or in this particular case, a formal positive charge, and the oxygen on the right-hand side has a negative charge. So we have these dipolar situations. So a 1, 2, 3, so 1, 3 dipolar reagent. And we're going to see, as a matter of fact, diazo compounds are also 1,3 dipolar reagents, and sometimes they can add across pi bonds in a similar fashion to ozone if you don't add heat to them. So that's kind of a cool little thing. If you review the Lewis structure of diazo compounds, you'll see the carbon has a negative charge, the nitrogen has a positive charge, and so you can get addition reactions very similar to that of ozone without heat. Now, because of this 1,3 dipolar character, what happens is it adds to alkenes to form a 5-membered ring. That the two carbons of the alkene are going to react with the 3 oxygens of ozone to form a 5-membered ring. So we've seen a lot of 3-membered rings so far. We're now going to look at 5-membered rings. And how does that happen? Well, again, I'm going to take the resonance structure of ozone, showing the positive charge on the oxygen, the negative charge on the other oxygen. Of course, I don't necessarily have to use this particular resonance structure. I could use one of the more major resonance contributors and just recognize that a pair of electrons is going up to the oxygen. And so I'm now reacting this with an alkene. The alkene adds to the oxygen. Now it would be on the left-hand side because it's the electrophilic portion of it, and the oxygen on my right-hand side is going to donate its electrons because it's the nucleophilic portion. So so in ozone I have an electrophilic end and a nucleophilic end, and the result is a syn addition. Right, it's adding on the same side, obviously, and we get something that looks like this. Right. So this is what is referred to as a primary ozonide, And this type of reaction is, the general term for this type of reaction is called a 3+2 addition. We've seen a lot of 2+1 additions, and now this is a 3+2, or sometimes it's referred to as a 2+3 addition. Doesn't really matter, okay? All right, now, one of the things to understand is primary ozonides, not so stable, right? And generally speaking, they quickly convert to an ozonide. So we go from a primary ozonide to an ozonide. What's the difference? Well, here we have a primary ozonide, and it's going to go to an ozonide. So primary ozonide to an ozonide. Notice the difference. Well, the difference is where the oxygens are located. So how did I insert an oxygen in between the two carbons? This mechanism is kind of a cool little mechanism, and it obviously involves a rearrangement, and that rearrangement involves a pair of reverse 1,3 dipolar additions and then forward 1,3 dipolar additions. Let's see how that happens. So the first step, we take our primary ozonide. And in that first step, what we're going to do is we're going to break the carbon-carbon bond, and we're going to form a carbonyl. Now, that once we start donating electron density, that oxygen-oxygen bond is relatively weak. And so I'm going to break that bond, and the electrons are going to go into the oxygen. So notice what I get from here. I get a carbonyl compound, and I get this species right here. So I get a carbonyl, and this is what is referred to as a carbonyl oxide. Do you notice anything about the structure of a carbonyl oxide? So this is what is referred to as a reverse 1,3 dipolar addition. Why? Because I've gone from a neutral primary ozonide to a 1,3 dipolar reagent, right? The carbon has a positive charge, the oxygen has a negative charge on it. So this thing can react again. How is it going to react though? Well, the way we have to orient it is we actually have to flip the carbonyl oxide over. So I'm going to take my carbonyl compound, I'm going to flip it over, flip the carbonyl oxide over. Why? Because carbonyls are polar. The oxygen withdraws electron density. It is nucleophilic. The carbon is electrophilic. So if I look at my carbonyl oxide, the carbocation is electrophilic. It's going to react with the nucleophilic portion of my carbonyl. And the oxygen that has a negative charge is going to react with the positive side of the carbonyl. And so I get this, right? So the oxygen donates electron density to the carbon. That carbon-oxygen pi bond then goes to the carbocation. And my result looks like this, right? So here is my ozonide. And that's basically a cool little mechanism to show the transformation of the primary ozonide into the ozonide. Now, generally speaking, ozonides can be isolated, but there isn't a whole lot of utility in ozonides. However, there is a synthetic usefulness to ozonides because they can be transformed to carbonyl compounds. Now, notice in the mechanism of going from the primary ozonide to an ozonide, we form a carbonyl compound. If we can simply break that ozonide up, we can get carbonyls. The way we do that is through either reduction or oxidation. So ozonides can be reduced using hydrogen over palladium on carbon. We can also reduce them using zinc. We can also reduce them using dimethyl sulfide. And when we do, they yield ketones or aldehydes. And that simply depends on the kind of nature of the alkene, the substitution nature of the alkene. Why is that? Well, if I take a look at some generic alkene where I have 4 groups and we don't know what those 4 groups are, I react it with ozone, to produce my ozonide, and then I reduce. I reduce with, hydrogen over palladium or zinc or dimethyl sulfide, any one of those. And so what happens? The net product is I essentially cleave the carbon-carbon double bond, and I produce two carbonyls, carbon-oxygen double bonds. So I get something that looks like that. And if you simply, understand the net result of it, it makes it pretty easy to kind of figure out. Okay, so this gives me carbonyl compounds. Now notice gives, I not specifying ketones or aldehydes because I don't know what's attached to the carbon. If any one of the carbons has a hydrogen attached, it's going to form an aldehyde. If there are two R groups attached, it's going to form ketones. So, as an example, here I have an alkene. The carbon on the left-hand side has two R groups. The carbon on the right-hand side has one R group, methyl group, and a hydrogen. When I treat this with ozone, followed by reductive workup with zinc and water, then the carbon on the left-hand side, it forms a carbonyl with two methyl groups. This is acetone. The carbon on my right-hand side also forms a carbonyl with a hydrogen and a methyl group. So you see that so I get, in essence, two products here. The one on the left-hand side is a ketone because there are two R groups. The one on the right-hand side is an aldehyde because there's an R group and a hydrogen. So you see that it's solely dependent on the structure of the alkene. Now, we can also oxidize ozonides, generally with hydrogen peroxide, and this yields either ketones or carboxylic acid. So instead of aldehydes, we get carboxylic acids if there is a hydrogen on one of the olefin carbons. As an example, here I have an alkene. On one olefin carbon, there's an ethyl and a methyl group. On the other olefin carbon, there's a methyl and a hydrogen. So I treat that with ozone followed by oxidative workup with hydrogen peroxide. I get a ketone and I get a carboxylic acid. So in this particular case, it's acetic acid. Now, one little twist to this type of reaction that chemists love to do is taking a cyclic alkene and reacting it with ozone followed by some workup. So in this case, I have a reductive workup. So the key to this is recognizing the reductive workup versus the oxidative workup. So here I have a reductive workup, and what happens? Well, remember, I break that carbon-carbon double bond. But when I have a ring, the carbons are still attached to one another, right? So if I think about numbering my ring 1, 2, 3, 4, 5, 6, then I can see that it's going to, the ring basically is going to open up and things are going to be attached. I still get two carbonyls, but they're attached to one another in this case. So how do I draw the structure of that? Well, I can draw, my 6 carbons. And then I say, well, what's attached to those 6 carbons? Carbon number 1 has a methyl group attached to it and a carbonyl. Carbon number 6 has a hydrogen attached to it because we're in reductive workup, and a carbonyl. So I get on one side a ketone, on the other side an aldehyde. Now notice if I take that same cycloalkene and react it with ozone followed by oxidative workup, what would I get? Well, I get the same thing, except instead of an aldehyde, I would get a carboxylic acid. So the structure would look almost identical except for the carboxylic acid side. And that's how you do ozonolysis followed by either reductive workup or acidic workup. Now, another reaction that's kind of similar to ozonolysis is oxidation with either potassium permanganate or osmium tetroxide. And the reason is because these two reagents will also undergo that 3+2 cycloaddition with alkenes. What does that look like? Well, if I draw the Lewis structure of the permanganate anion, I get this particular structure, right? Manganese has three oxygen double bonds to it, and one oxygen that has a negative charge, right? That's the most stable Lewis structure of permanganate anion. And so when it reacts with an alkene, I'm drawing all the electrons around it, what's going to take place? The pi bond of the alkene donates to one of the oxygens. The electrons from that oxygen manganese bond go to the manganese, and then I take another pair of pi bonds and insert them into the carbon, and I get this particular structure, which is relatively unstable, and we're going to see what we can do with it, right? And of course, likewise, I can do this with osmium tetroxide. This is the Lewis structure of osmium tetroxide, and we can see kind of a similar type of structure. When I react it with an alkene, I get that 3+2 addition, and the result looks like this, right? So this is the type of reactions that the permanganate or osmium tetroxide make with alkenes. Now, generally speaking, none of these are isolated because, especially in the case of the addition with the permanganate, you can easily hydrolyze them. And when you hydrolyze them, notice I've created two carbon-oxygen bonds. In the presence of water and a base, what happens is you get hydrolysis. And so you retain those carbon-oxygen bonds, and the manganese gets hydrolyzed, and you form diol. So let's take a look at that reaction, right? You typically don't isolate the adducts of that, but you form vicinal diols. So I take my alkene, react it with potassium permanganate and sodium hydroxide, and I'm going to get a vicinal diol. Now the key is that, and why do we go through the hassle of thinking about the formation of those adducts? Well, just like in ozonolysis, there is a syn addition, so there's stereochemistry involved. And upon hydrolysis, the result is a vicinal diol, and the two OH groups are cis to one another in essence, right? You get a syn addition. And that's a key component. We've seen how to make vicinal diols already with epoxides, right? Ring opening reactions of epoxides. Those products are always anti-addition because it's an SN2 mechanism, and so the OH groups add on opposite sides of one another. In this reaction, I'm taking an alkene, reacting it with permanganate in sodium hydroxide and water, and I get syn addition. So I now see how I can control stereochemistry of my reaction. So here I'm taking 2-butene, reacting it with KMNO4 and sodium hydroxide water at some low temperature, generally speaking. We have to do this at low temperature because if not, we can actually cleave that bond. And I get, again, syn addition. So I get this, and of course I get the enantiomer of this, which is a meso compound. So, okay. I'm sorry, it's not a meso compound. It would be the enantiomer of this. All right, so again, I can take cyclohexene, treat it with KMNO4 sodium hydroxide, and I get cis cyclohexane diol, cis cyclohexane diol. Now notice I haven't used osmium tetroxide here yet, and the reason for that is because the osmium tetroxide ester that forms is actually quite a bit more stable than the permanganate ester that's formed. And so you need to actually hydrolyze it with a reagent like sodium sulfite, right? So generally speaking, we use sodium sulfite in this process, but the net result is the same, right? You react it with osmium tetroxide, followed by sodium sulfite and water, and you get the OH groups adding across the double bond. And in this case, they're both on the same side, right? Syn addition. So I would get this. Of course, there's a plane of symmetry here, and so it's a meso compound, and I don't really have to worry too much about the stereochemistry of this. Okay. Here I have a cis, right? Alkene reacting with osmium tetroxide, followed by the sodium sulfite and water, and I get again syn addition, right? And in this particular case, I would also have an enantiomer forming. So you see the utility of the reaction of alkenes with permanganate or osmate is forming our vicinal diols that are syn, right, cis to one another. They're on the same side, so syn addition versus anti-addition. And being able to control stereochemistry is now becoming vitally important.